Hi, I'm Unik. I will be doing a screencast with commentary of Encoder Beginner Contest 418. The contest has already started, so let's just jump right into it. 7 problems. Problem 8. Takahashi is a teapot. Since he's a teapot, he will gladly accept tea, but will refuse any other liquid. Determine whether you can pour a liquid named S into him. Given a string S, determine whether S is a string that ends with T. Okay. So yeah, the first 2, maybe 3 problems are just simple coding exercises. So if the length of the string is at least 3 and the last substring of the last 3 letters is T, we need to output yes, otherwise no. I mean, I'm pretty sure I didn't make a mistake in this amazing program. So I could have just submitted. Okay, now we are a teapot. I begin with T and end with T, and I am full of tea. What am I? Okay. For string T, define the filling rate as follows. Now the first and last characters of T are both T and the length is at least 3. Let X be the number of T in T, then filling rate of T is X minus 2 divided by the length of T minus 2. Otherwise, it's 0. Given a string, find the maximum possible filling rate of a substring of S. Okay, the limitations are so small that we can just try all the options and apply the definition. So I will just iterate over all substrings. Calculate the function from the substring. I don't know how to print doubles with cout, so okay, so first of all, our string must have length at least 3. If n is less than 3, return 0. Then we need to check that the first and the last characters are T. If the first character is not T or the last character is not T, we also return 0. And in this case, we need to calculate the number of occurrences in T. And we return x minus 2 divided by n minus 2. And it doesn't work. Amazing. Oh, n is not given. Problem C, flush. On the poker table, there are T bags. What's up with this contest in T? Tea bags of n different flavors. The flavors numbered from 1 through n, and there are AI tea bags of flavor I. You'll play a game using these tea bags. The game has a parameter called difficulty between 1 and the sum of all AI inclusive. A game of difficulty B proceeds as follows. You declare an integer x. Here it must satisfy B. So x must be between B and the sum of all AI. The dealer chooses exactly x tea bags from among those on the table and gives them to you. You check the flavors of the x tea bags you receive and choose B tea bags from them. If all B tea bags you choose are of the same flavor, you win, otherwise you lose. The dealer will do their best to make you lose. You're given Q queries, so answer each of them. The J's query is as follows. For a game of difficulty BJ, report the minimum integer x you must declare at the start to guarantee a win. If it is impossible to win, report -1 instead. Okay, so this is a simple problem. We have array AI. So how to solve one query, right? We are given B. And basically we want to find the largest number of tea bags cards the dealer can give us so that no B of them are the same. So obviously of every type I, the dealer can give us minimum of AI and B -1 tea bags. Because if he gives more than that, then well, either it's impossible because there wasn't that many tea bags of that flavor, or we will be able to pick B of them. So for a query, we need to output the sum of minimum of B and AI over all I. But also if B is strictly bigger than all AI, then it's impossible. We need to print -1 because like the dealer can give us all the tea bags and we still won't be able to take B that are the same. Okay, so guess first we will mm, just find the maximum of AIs and like deal with this -1 by comparing each query B with like maximum of AI. So now if the dealer gives us all the cards, it is possible, and we just want to calculate some of those minimums. And so let's sort the array I, the array A. Then for a query, there will be like small flavors where there is not enough T-bags, like the minimum of B-1 and AI will be AI, and those will be first in the sorted order. So there will be like a prefix where we are interested in the sum of AIs, and there will be a suffix where we are interested in just the number of them, and then we multiply it by B-1. So to find the separation point, we will use binary search, like lower bound. And to get the sum of AIs on the prefix up to the separation point, we will precalculate all those prefix sums. That's it. So read the array A, sort it, then calculate the prefix sums. And now for each query, read B. If B is greater than the maximum of them, but since we sorted the array, the maximum is just the last element, we print -1. Otherwise, we find the separation point. B or B-1, anyone will do. Now the answer is f of p plus n minus p divided by b. Need to cast too long here. That's it. so yeah, here I need to multiply by b minus 1, but also I need to add 1 because like this is the maximum number of tea bags the dealer can give us so that we lose, so the minimum number to win is this plus 1. Okay, now it is correct. And also correct in the second sample. So I can submit. It was 300,000, right? Problem D, XNOR operation. This problem is a sub-problem of problem G. Interesting. Well, I guess we'll see that when we reach problem G. A non-empty string S consisting of zeros and ones is called a beautiful string when it satisfies the following condition. You can perform the following sequence of operations until the length of S becomes 1 and make the only character remaining be 1. Choose any integer I satisfying I is between 1 and the length of S minus 1. So I guess we will take like 2 consecutive characters and then apply the sum operation to them and replace them with 1 character. Define integer x as follows. So yeah, basically this just defines a particular function of 2 bits, and it's like XNOR function, but XNOR is just equality, right? Like if the characters are equal, the result is 1, otherwise the result is 0. Remove si and si plus 1 and insert the digit corresponding to x in their place. You are given a string t of length n consisting of 0 and 1. Find the number of beautiful strings that are substrings of t. Even if 2 substrings are identical as strings, count them separately if they're taken from different positions. So actually, like, this is bad way to say that. Like, you need to say find the number of like pairs LR such that like the given substring is beautiful, because this is very particular. It says find the number of strings that are beautiful and substrings of T. So like if the same substring is in several positions, you should count it once according to this. But then, like, they say specifically that that's not the case. We just wrote the statement wrong and then made it right. Okay, so we need to find the number of subsegments that are beautiful. So like it should be possible to perform such a sequence of operations. I think the parity of the number of zeros stays the same, right? Like this operation removes 2 zeros. All the other operations do not change the number of zeros. So if the number of zeros is even, then we will end up with a 1 no matter the order of operations, and if it is odd, then we will end up with a 0. So we just need to calculate the number of substrings in which there is even number of zeros. To do that, we will calculate prefix XORs basically, and then like the substring is good if the prefix source on the end are the same, or like prefix sums are the same parity. No, that's wrong. I need to change zeros to ones, like swap them, and then I'm counting the number of zeros. So I'm calculating the prefix sums for the number of zeros, and then the prefix sums on the end must be the same parity. So we basically say that 0 gives us +1, 1 doesn't give us +1, then we calculate prefix sums. Then we count the number of even prefix sums and odd prefix sums, and for each of them, I just need to take two different positions. So it's the number of even prefix sums, choose 2, plus the number of odd prefix sums, choose 2. So I'm just going left to right. If the character is 0, then I'm increasing the balance. And if the balance is odd, then I increase B, otherwise I increase A. So A counts the number of even balances, B counts the number of odd balances. And I made them long, despite like both of them are clearly at most n plus 1. But now I want to take like that number, choose 2, and like here I can have overflow. So since the problem G is called binary operation, I'm assuming like instead of XNOR, the operation will be given or something. For each of them solves the following problem. Okay. But we have two more problems before that. Problem E, trapezium. There are n points on two-dimensional plane with i's point at coordinates x, I, y, I. It's guaranteed that no 2 points are at the same position and no 3 points are collinear. Among the combination of 4 points from these points, how many combinations can form a trapezoid as a polygon with those 4 points as vertices? Is there a definition of trapezoid for me? Note that parallelograms and rectangles are also treated as trapezoids, which is like not obvious, and like it's not like that in all the countries basically. Just as like 0 can be like a natural number or not in different countries. In different countries, trapezoids can include or exclude parallelograms. So I guess this problem specifically asks us to calculate the number of polygons on 4 of the given vertices such that they have 2 opposite parallel sides. But still, would be nice to have a definition of trapezoids, because like it's not exactly the I mean, it's a common geometrical term, but it is not the same in all the countries. So probably should have given definition. Okay, so no 3 points are linear. This is very nice. It just means that if I have two segments that are parallel, like I can take them as opposite sides because they cannot lie on the same line. So I can try to count the number of like pairs of parallel segments, but there will be an issue still with parallelograms because parallelograms have two pairs of opposite sides that are parallel. So if I just count the number of pairs of parallel segments, I will count all the trapezoids, but I will count the parallelograms twice. So I need to subtract the number of parallelograms after that. So now I need to calculate the number of parallelograms that I can make on those endpoints. And that is a standard problem, but the solution is pretty nice. So one of the ways to define a parallelogram is quadrilateral, which diagonals intersect at their midpoints. So for parallelograms, we will I will try to find pairs of diagonals such that their midpoints are the same. So basically, I will iterate over all the segments again. For every segment, calculate the midpoint, and then like in a map, basically do a plus plus in that point. And then for every point, I calculated for how many segments that point is a midpoint. Now, if I take two different segments for which this point is a midpoint, I state that those four are parallelogram because like I can take those segments as diagonals, and because again no 3 points are linear, those two segments will not be on the same line. Actually, they will actually like intersect in that midpoint, in their common midpoint, and they will form a parallelogram. So basically I need to like two times I need to group the segments by some common characteristic, and then for every like group with that common characteristic I just choose two segments. The first common characteristic is like whether they're parallel, so like I'm interested in the like direction that segment is in. I need to be like slightly careful. Basically, I want to take a vector and normalize it, and that will be my characteristic. But I need to also make sure that like the vectors that are opposing also will be the same. So I will make sure that, for example, like x coordinate of my vector is positive, or it is 0, but y coordinate is positive. And since everything is integer, I can like normalize in integers. That's like n square GCDs, which is n square log, but I guess it should be fine. The number's not that big. But yeah, like GCD is not very fast because like you're repeatedly doing like module operations and not that fast. So like need to be slightly careful here. Yeah, so have my endpoints, iteration over all the segments. taking the like direction vector and grouping. Basically, I can throw in map by z, but I don't want to do that because maps are slow. So instead, I will just put them in one big array, sort it, and then find the segments of equal elements and like count the size of each group that way. And then do the same for midpoint. Also, like midpoints, like how to calculate midpoint, you take like sum of coordinates and the divide by 2. You don't want divide by 2, but like you can just not divide by 2 for all of them. Basically the same as like multiplying all the coordinates by 2 and then taking midpoints. The grouping will be the same, but now you're staying in integer values, so that's good. Okay, let's do that. I'm not even going to use like struct point. Just deal with them as like numbers. So the sizes of my like big arrays must be like of the order n squared, but it's actually like n squared divided by 2. Okay, so the easier part is the midpoint. So it's make pair a I0 plus a J0 and a1 plus a J1. Okay, the normalized direction is a bit harder. Calculate GCD. When you calculate GCD, you want to have non-negative values. If x is not 0, then I want to make sure that x is positive. So if x is negative, take the opposite, and if x is 0, then if y is negative, so take the opposite, and now this is the vector we want, and plus plus. So now I just want to find segments of equal values. So I have a group of x equal values, like group of segments that are like the same by that characteristic. In this case, the characteristic is the direction of the vector, so those segments are parallel, and I can take any two of them to get two parallel segments that will form a trapezoid. But as I said, like we calculated parallelograms twice, so that now we need to remove them. Basically doing the same thing, but now with array C instead of array B. And we need to subtract it from the answer rather than adding. Weird teapots. I think they should have like stuck to it and add T in every problem, because like problem C is clearly not like about T. A and B, yes. Okay, problem F. There are n teapots ranged in row numbered from 1 to n from left to right. There is a sequence of integers a1, so on an, initially with values -1. You will fill each teapot with either tea or coffee, blasphemy, so that the following conditions are all satisfied. For any two adjacent teapots, at least one of them contains tea, or thank God. For any integer I satisfying I from 1 to n, if ai is not -1, then exactly ai of teapots from 1 to I contain coffee. Okay, and I guess we will fill in those that array with queries. You are given q queries, which you should process in the given order. The j's query is as follows: change the value of axj to yj, then print the number modulo of ways to fill the teapots satisfying the conditions. And the values yj can be -1, and we can rewrite the order. Okay, interesting. Why is it initially -1 then? Like, I thought because of that, I thought that we will only change -1 to not -1s to not -1s. But like that's not the case. Interesting. So we need to count. Let's say that AI is just given. As always, I first want to understand how to answer one query before jumping into doing queries. I don't know how to solve like the last query basically. I got runtime. Get runtime. The hell? Oh. Okay, that is runtime for sure. back to problem F. Need to count the number of binary strings. Let's say the tea is 0 and coffee is 1, so we cannot have two ones next to each other. And we are given some prefix sums. Well, it feels like so we are given some prefix sums. Obviously, we know that prefix sum at the start is 0. We are also given some additional prefix sums. That just means that we know the number of ones on every segment here. They're not exactly independent. Because we cannot have ones on both sides of the split. Well, with some data structures I don't want to write, I can solve. So we could do okay. So if we want like slow solution for one query, like not even linear solution for one query, we could do dp prefix sum and last. We building the string of zeros and ones from left to right. Let's say we have built it prefix of length p. We have taken like this number of ones, and we're also starting the last element because we need to make sure that we don't take two ones next to each other. So we can calculate this dp left to right, and for the places where we know the prefix sum, we just check that basically we zero out all the states that do not have correct prefix sum. Okay, but that works in like quadratic type. How can we try to do it better? Well, to do it better, I want to jump like only through the only through the points where we know the prefix sum. The idea there being that if I only jump in through them, I don't need to store the sum in the dp value, because like in all the points that I'm jumping through, I know that sum. But now, basically, I need like the following subproblem. Let's say I'm standing here. I want to jump here. So I have like dp I0 and dp I1 here, because I'm not storing sum, because it is fixed in this point. But now I need to jump here and find those DP values. To do that, I need to calculate the number of transitions between those pairs of states. So I need to calculate basically 4 transitions. Those 4 transitions being, so I start with like either 0 or 1 here. I want to end with either 0 or 1 here. Here I need to use the given number of ones. And I want to know like how many ways are there to do this. I think that number of ways should be like a binomial coefficient. Always like with like we need to be somewhat careful, but basically the idea is that after 1 there always must be 0, so we can say that we are not placing zeros and ones, we're placing like those pairs 1 0 and then just zeros. So this is not like exactly true, because there can be a 1 on the end, but like if we are in this situation, we are not like the characters that we are putting there are not at the end. There always will be a next character, so those are like 1 0 and 0. So if we want to like have 0 here and 0 here, let's say this length is L and I want S ones. So here I'm saying that, okay, that 0 was the end of group, like either of this type or of this type, and this 0 will also be an end of a group, and so I want S groups like this and L minus 2S groups like this, and I can put them in any order, so the number of ways to do that is L minus 2S plus S, choose S, so L minus S, choose S. Okay, if I want 0, 1, this is L. So again, this was the end of the group, but this will be a beginning of like 1 0, or maybe it like maybe there are just ends here. But it doesn't really matter. What matters is that, well, obviously S must be at least 1, because I have this 1 that I want. But now, like in this area, I want S minus 1 groups 1 0 and still L minus 2 L minus 2S plus 1 groups just 0. And so the number of ways will be L minus S, choose S minus 1. Okay, if it's 1 and 0 here, that just means that after this 1 there will be a 0. This will be that group. And now here on L minus 1 elements, I want S more groups like this, and therefore like L minus 1 minus 2S groups just 0. So the number of ways will be L minus S minus 1, choose S. And the last one is like 1 here, 1 here. Like this. And on those L minus 2 remaining positions, I want S minus 1 groups like this, and L minus 2S groups like this. So it's L minus S minus 1, choose S minus 1. Great. So now I know all my transitions. Binomial coefficients, like I can pre-calculate factorials and take binomial coefficients in constant time. So now if I just want to answer one query, I can do all those jumps, and that will be like linear time. But now I have queries. Well, like it's certainly doable if I like store this in like I don't know a trip. Basically, like my transitions are like multiplying by a matrix with those values. So like every segment corresponds to a matrix. Except, yeah, okay, there is also like a suffix in the end where, like, in the end, I might not know the prefix sum. So, like, from there, I need to do something different. But I still don't care about the sum. So I just need to pre-calculate basically, like if I start from 0 and if I start from 1, just calculate like 1 dp like this without storing the sum, because we will not care about it at all. And so like I calculate this dp once in linear time, and now I know like how many ways there are to finish my sequence if I end it on 0 or if I end it on 1. And those numbers will be Fibonacci numbers. I'm just throwing it in there. So yeah, if I'm storing like all those matrices in some kind of trip, then I can like process all the queries. Basically, the query is like changing a constant number of segments, like taking them out or inserting them back. But that's I certainly don't want to write that. This is called a beginner problem. Not even the last problem. Maybe I'm missing something obvious. I can probably use like some kind of square tight composition instead of trip. Well, it will be like slightly easier to implement, but still. Um, you don't really see another way. 40 minutes. Looks like looks like that's what they want. But I was wrong on that the last time. Do people solve it? 31. 11 minutes. Pretty fast. But yeah, mostly people struggle with it. But like, I'm not sure, like, without explanations, that I would be able to uh, do it in like 12 minutes. I don't know. It seems unreasonable to me. Like, in 25 minutes, yeah, probably. But in 12? Don't think so. Well, Kevin took 26 minutes. Maspai took 25 minutes. So maybe maybe it's what they did. Okay, let's look at problem G. I don't want to implement it. I mean, it's certainly easier to do if you have like pre-written matrix and pre-written like good trip or like some kind of like set with operations. And it's not that bad. I don't have a good pre-written. I have some pre-written trip, but it's kind of not great. Problem G is the same as problem D, except now we need to solve it not for XNOR, but for all 16 binary functions. And we still need to count the number of segments such that it is possible to like consecutively like take two elements, apply the operation to them, like do that until you're left with one element, and you need to get a 1. And well, it feels like there is you just need to like hard code 16 like functions. Like most of them are simple, right? And like there is a lot of symmetry. So this is super easy. Like every applicational function gives the 0, so the only way to get a 1 is not n. The only way to get 1 is just take a segment that was a 1 at the start. Zero 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 one is yeah, for notation, what I'm saying is like this is the result of applying to 0 zeros and 0 1 1 0 and 1 1. So this is AND function, and so we need the number of segments that only consist of ones. That's easy to calculate. 0 0 1 0. So we get a 1 only if it's 1 0. So we certainly want a 1 at the start, because if we have a 0 at the start, we will always have 0 at the start. So we want a 1 at the start. We do not want just 1 1, but other than that, it feels like probably for long enough sequences we will always be able to do. So if we have a 1, yeah, if I have a 0 somewhere, if I have like a lot of 1s and 0s and then something, This I can make into 0 just by like this 0 can eat everything. And then I can actually not true, right? If I have like 1 1 0, that's bad. If I do like this 1 1, I will get 0 0, and that's bad. If I get this 1 0, I will get 1 1, and that's also bad. So I want to get a 0 after my 1. If I can get a 0 after my 1, that's good, because then that 0 can eat up all the suffix, and then I will get like 1 0, which is good. So if I have actually like 1 1 1 and then something, I can like apply the operation to those two ones and get 1 0 and then something. That's good. If I just have like 1 0, it's also good. So the remaining case is when it's 1 1 0 and then something. Maybe this is just bad. No, it's not always bad. If I have another 1 somewhere, I can eat up those zeros one by one, look into that one. And then I will get 1 1 1, which is good. Okay, so if I start with 1 1 and I have another 1 somewhere, it's good. So the only possible bad case I'm left with is 1 1, but then all zeros. Yes, this seems bad, because I cannot use this 1 while there is 1 to the right of it. If I use 2 zeros, I just remove one of them. If I use this 1 0, I remove the 0. So in every operation, I will just remove a 0, and then I will be left with 1 1. This is bad. Okay, so I need to count the number of segments that start with 1, but not like this, not 1 1 and then just zeros. Should not be that hard. Like, I can just count the number of segments like this and then subtract the number of segments like this. This is super easy, and this like shouldn't be hard. If I get if I like compress the groups of consecutive zeros ones, then this can happen only on on the border between two groups. Group of ones of length at least 2, and then group of zeros, and like for every such place I just need to add the length of group of zeros to the answer that counts everything with zeros, and I also need to count the number of just 1 1. That's also easy. Uh, okay. So the next one is 0011. This operation just keeps the left element. Right? Like if the left element is 0, then the result is 0. If the left element is 1, then the result is 1. So no matter what you do, the result will be the left element, so just the number of segments that start with 1. That we already did for the previous one. 0, 1, 0, 0. That seems like similar to this. It's basically like reverse the string and then solve this case. So same as 0, 0, 1, 0. 0, 1, 0, 1. This keeps the right element. So it's just the segments that end on 1. Also, yeah, I guess if two functions only different like by swapping those two elements, it means that I just need to reverse the string and solve the other one. So this is like this but reversed. 0, 1, 1, 0 is XOR, and it should be solved as problem D was solved. Like in problem D it was XNOR, but like if I want, basically like the parity thing still works, right? The parity of ones will be the same, so we need to count the number of segments with odd number of ones. So this is XOR and like same as problem D. 0, 1, 1, 1 is OR, and OR should be, well, the same as AND, but also I can just say that it's number of segments with a 1 somewhere. So not segments that are not just zeros. Okay, and when like there is 1, there should be similar to this. Basically, I can invert all the elements, and now I want to get a 0 instead of 1, so it's like total number of segments minus the answer to like corresponding problem here. Great. I still would rather implement that rather than F. It's not great either, but what's L and M? L is the length of the longest beautiful string. Why? For the longest, I cannot just inverse and then take like minus whatever, and like here minus. I also cannot just take. Also, inversion is not true. Okay, I guess I have to solve another 8 cases. Maybe there is actually like a good solution that doesn't doesn't consider 16 cases. But I don't know, like it seems pretty specific. Like for the function I need to say if it is possible to get a one, not just like implement the operations in some order, but like I need to say if it is possible to choose the order, and the way I'm choosing the order of operations is like different for different functions. One zero zero zero. So it's like NOR function. This is actually unclear how to do it all. I want to get one in the end, so it must have been produced from 2 zeros. Okay, so on previous level, like 000 is bad, because I would get like either 10 or 01. If I have just one, it is good. I can merge that one with one of the zeros, get 0, that's good. If I have all 3 ones, that's bad, because on the next level I will not have 0. If I have 2 ones, it's bad if the 0 is in the middle, but if it's not, it's good. So 110 and 011 are good. This kind of feels like there is like a lot of freedom. So hopefully, like with a long enough string, I can get more or less anything. Um, like I would hope that if string is long enough, then I can always get one, or at least like the patterns for where I cannot get one are very restrictive. Okay, so 0, 0, 0, 0 is good. If I have just one somewhere, I think I can get either this or this. So if I have like this, I can merge those two zeros into ones and get this one. If I have 0, 0, 1, 0, I can merge those two zeros and get this one, and reverse is also good. So just one is good. If I have all ones, that's also good because I can take those and make them into 0 and get this one. If I have just 1, 0 and 3 ones, this is good because I can take two ones, make them into 0, and that will this will be just one, and I can always do that if I have 3 ones. Okay, now the ugliest case is when there are 2 ones and 2 zeros. Zero, 0, 1, 1. I will take. I can always take 0, 1 that are neighbors. They will become 0, and I will just have one left. So that's good. Okay, so all the strings of length 4 are good. Therefore, all the strings of length more than 4 are good. So there is just a fixed set of bad strings. And all with length at least 4. 0, 1, 0, 0, 1 is problem D. 1, 0, 1, 0. So this like takes the right character but then inverses it. This feels also good if the string is long enough. So if the string is long and ends with 0, we can just do some operations to make this into one character. We don't care whether it's 1 or 0, then we just apply the operation to this and get a 1. If the string is long enough and ends with 1, we will first apply the operation to the last two characters and get to this case. And that's it. So long enough for this case is anything longer than 1. Long enough for this case is anything longer than 2. So, like, bad strings are 0, 0, 1, and 1, 1. All others are good. 1, 0, 1, 1. So if I can get a 0 in the end, I'm good. Like, similar to this, I can just take the remaining, do the operations until it's one character, and then I will have something 0, and the operation to them gives me a 1. If I have a 0 somewhere, I can look at the last 0. After it there are ones, and now I can eat those ones. 0, 1 makes it 0, and I get this case if I have something here. So if I have a 0 which is not in the first position, I'm good. So the only two cases where I might be bad is 0 and then all ones, and just all ones. Just all ones is good because it will stay all ones, and 0 and all ones is bad. Right? It will always stay like this. So bad is 0 and then all ones, and that's it. All others are good. 1, 1, 0, 0 is the same as this, but like reversed. So bad will be 0, 1, 0, and 1, 1. 1, 1, 0, 1 is this, but reversed. So bad is all the ones and then a 0. 1, 1, 1, 0. So this is NAND, and it should be similar to this. So I'm also like assuming that all long enough strings are good, and there is just some small number of bad strings. And like 1, 1, 1, 1 is just only 0 is bad, everything else is good. And for this one, I again need to do the. I mean, it probably would be faster to do it on a computer. And again, I don't know how Spy solved it in 20 minutes. Like, I needed like half an hour to just write all the cases on paper. Then I would need to code like 16 functions. Each one is pretty simple, but still. Okay, so for this case, if I have like for length 1, only 1 is good. For length 2, 0, 0, 0, 1, and 1, 0 is good. And I mean, that should be cool, right? No, actually, 1, 0, 1 is bad. 1 is bad. 1 0 1 is bad. But all others are probably good, right? If I have two ones next to each other, I can merge them into a 0, and that's good for lens 2. If I don't have two ones next to each other, it's either this, which is bad, or it is just one somewhere, but then I can keep a 0. Basically, yeah, if I can keep a 0, it's good. So the only case when I cannot keep a 0 is like when both border characters are ones, but if it's 1 1 1, then I can make a 0, but if it's 1 0 1, I cannot. Right, so now the only potential bad string would be 1 0 0 1, because with every operation I must get 1 0 1, but that means that my string starts with 1 0 and ends on 0 1. But that is not bad, because I can take two middle elements and make them into a 1 and get 1 1 1, which is good. So the bad strings are 0 1 1 and 1 0 1. Okay, great. I'm not implementing that either. And then I have like 8 minutes left. 5.5 minutes left, because I started later. So why at Coder beginner contests are harder than second division contests on Cat Versus? Like previously they had like last problem was like educational on some non-standard topics, so okay, that one might have been hard. Although like this problem is not about any particular topic. And this, I mean, kind of, well, at least with my solution, it's a bit of implementation hell. It can be written in like 15 minutes probably. And if you have more pre-written code, then faster. But this is just insane. I'm probably missing something again. Okay, at Coder is just way too hard. First I'm solving 0 on at Coder Grand Contest, and then I cannot solve at Coder Beginner Contest problems. That's great. Alright, thanks for watching.